All right, good morning, everyone. So let's start with the last quiz. Now, whenever you're seeing any kernel visualization online, what are you looking at? What basically we're saying, if you go online and write kernel as a CNN visualizations, you're going to get a bunch of images. What are these images? Yeah, they are features. You're not looking at how kernel looks like. You're trying to see exactly what the kernel is extracting, right? So there's a difference there. You understand that? You understand what is the difference between what kernel is extracting and what is a feature map? Anyone? What is the difference?
So feature map is the output layer of what kernel is extracting.
Same thing.
No.
What kernel is extracting in feature map.
No.
Kernel extract the features.
Huh?
When all features get at some point they can be plugged into one.
Yes, that becomes a map. Right? So when you're looking at what each kernel extract, this is what it can do at one particular convolution, for example, when it's not moving, right? So for the first one, when it's looking at 11 cross 11, that is what it is trying to see. So think of a kernel which extracts E. So that becomes what kernel extracts. If you run that kernel on the whole newspaper, you're going to see a bunch of E's. That becomes a feature map. So there's a vertical edge extractor which is going to extract a vertical edge. That becomes a feature, or that is what kernel is extracting. But when you use that kernel and run over the whole image, it's going to extract all the vertical lines. That becomes a feature map. It's a map of features.
So the first layer or second layer, the feature map will not have all the right features in that.
Repeat that.
In the first and second layer, the feature map, the output, will not have all the features of similar type. As we go on beyond
You'll start making extracting complicated features, features built on the simple features.
We don't have reattempt for quiz.
Reattempt for quiz. There's only one life. Okay, what do we need to consider when we decide the number of kernels in our 11 cross 11 receptive field? Right, first explicitly required. We're trying to see how complicated our data set is. Right. Second is inter and inter-class variations. For example, if you look at ImageNet, there are 1,000 classes and there are tons of dogs there. So you don't have to just look at a dog and say it's a dog, you have to say which dog is it. So you have to say it's a Vodafone dog or an Airtel dog or a Reliance dog, right? So, and the textures vary a lot. So that becomes the inter-class variation. When we talk about intra-class variation, we have a dog where you have fur kind of texture, but you have frog also, where the texture is very organic, it's very smooth, very transparent, right? And then you have metallic objects also, cars and airplanes, where you have shiny surfaces, where the glossiness of a shiny surface is very different from the glossiness you will find on a frog. So you have to have very different kind of kernel which can actually extract these textures and these features. Then we have the hardware capacity also, right? We may have a wish to make a deep neural network where we have like 1 million kernels, but your hardware can only support 512, so you have to be limited by the hardware. So in the end, it's a combination of these things. Now you look at the last one, total number of images in dataset. This is not the answer for this one. Why is that so?
So it depends on the one image, which is the particular size of kernel. So it is not based on the data set.
Yes, the reason it is not, because see, this is not the direct answer for this. Anywhere where you have a confusion whether it may be the answer, it may be the answer is not there. Because we are saying that this is a general truth. This is not a general truth. Look at the MNIST example, right? And as you proceed forward, you're going to see that you're going to be adding a bit of image augmentation also. So you're going to take this digit of 1 and rotate it slightly. You're going to take that digit 1, move it slightly, right? All of these images are same images. You just have a slight variation of these images that is not forcing us to increase the number of kernels also. In fact, on an extreme edge, imagine a database, let's say 1 million images, and imagine a network which works for that 1 million image. A very weird way of increasing data set would be to take this 1 million images and get a copy and get 100 copy of each image. Now a database 100 million images, but model is not going to change because it's exactly the same images. So this is on the extreme end, so where you do not need any capacity increase. Look at the other extreme where you have now ImageNet database where the classes are there, but now you're taking variations of different classes also. Now, when the complexity of database increase, then you need to increase the model capacity also. Now you're not looking at, for example, cars, right? You expect cars to be only on the road, unless you are looking at Rohit Shetty's movies, where the car is upside down also. So now suddenly the database has increased. Now suddenly you have to consider all of those scenarios. Humans are supposed to be walking on two legs, unless it is Ramdev Baba, who's upside down. So now again the model has a different expectation. So whenever your classes are going to change or the class variation is going to change, you have to increase, right? But increasing number of images is not a direct answer for that. We have to say increasing the variation of images in the database, right? That is why this is not a true answer. But you can think like there are two extremes. One just copying the same images, and other where you're going to be increasing the complexity of
What's the
database.
meaning of some
Sorry?
expressivity required?
Expressivity. This is how you're defining the second one. The second one we are saying variances, but it is actually expressivity. How expressive you want a network to be.
Okay.
In how many ways you want to define a particular texture, or how many textures you want to be able to figure out. Now select the ones which are true. If you use strides sometimes for resource constrained hardware, right? You're going to be using strides only when the resources are really less. Now this is going to be true till we are hitting the ResNet paper, which is going to be session 13 for us, right? So when you hit session 13, we are going to see that strides can actually be used as a part of another algorithm where we are not just looking at a constrained hardware. Then you may want to run strides on a very good hardware, but not on all the kernels. It's going to be very specific kernels, but not at this stage, right? Now we tend not to use strides as they do not reach spatial data evenly. They don't distribute the spatial data evenly, causing checkerboard issues. How many of you selected this because it had checkerboard issues, but the statement did not make sense? We tend not to use strides as they do not read spatial data evenly. Right? When you're looking at strides, you're going to be reading some pixels more and you're going to be reading some pixels less. If you go back to assignment 1, you will remember that you were supposed to make the blur kernel, and this is exactly what you did in your blur kernel also. You're trying to merge pixel values from different areas into a new pixel, right? You're bleeding the values, and this is what is going to happen if you're using any kernel with a stride of more than 1, where the checkerboard issue is going to be coming in. So whenever you have an algorithm where you have some bit of information read geometrically or in a fixed pattern more than compared to some other pixel, you are going to see this issue.
I think it says react.
Yes, it should be read. Yeah. The channel created after convolutions are blurry, not consistent.
I did this one also. Because it's blurry only.
Yeah, so what actually happened in the last session, people said that suddenly when they were looking at the last one, they forgot the context of the question, which is sort of true also, because if you think about that, I'm not asking you to think about I'm not asking you to think about strided convolutions here, right? So the title says select which all are true.
Yes.
Now when you read the last one, the channel created after convolutions are blurry. You're not linking it back to strided convolutions.
Yeah.
That is why the last one answer is supposed to be there, but I forgot to tell you that this is strided convolution. So you have a legal challenge that you're not telling me it's strided convolution, so last one may be true, may not be true.
So even if we add stride, it would be blurry.
Only if you add strided, it is blurry.
Otherwise,
It's not. Otherwise, it's a very clear channel.
even if stride is on, it won't be blurry.
No, it won't be blurry.
It would be right.
No, we are going to see that, and we are going to actually run code for that also.
Okay.
Right? Look at the last point. Last point is true if you're talking about strided convolutions. If you're not talking about strided convolutions, it is not true. So I made a score to be 0. So in case he selected it, it's not going to matter. It's still not going to matter. Now, what are the benefits of 1x1 convolutions? Lesser computation required for reducing the number of channels. Now, we need to look at this in different ways because we are going to be using 1x1 a lot many times. 1x1 is not considered convolution. Do you agree? Why is that? So even from the so what we are supposed to do in 1x1, we are supposed to look at this pixel multiplied with a 0.5 value, then again this pixel with same value, then this pixel with same value, this pixel with same value. So this looks like a repetition stuff, right? Now you need to know one thing about GPUs. GPUs have something called SIMD inbuilt, which is single instruction multiple data stream. What does it mean? Single instruction. Let's say you have to multiply something by 0.5, right? You take the RAM of the GPU and add, let's say, 0.6 inside. Let us say that this process is going to take 10 nanoseconds, right? Now you take the same GPU and inside add 0.6, but add, let's say, 10 billion of them. That is what the RAM of the GPU can support. How much time do you think it's going to take?
Same time.
10 nanoseconds.
Yeah. It would multiple. It will give 10
So, and this is exactly why GPUs are used for machine learning. You have one instruction, take one kernel, multiply with last data, which is all the channels which are coming in. That is why these are different from CPU. In CPU, this is going to be 10 nanoseconds into 10 billion. But on GPU, it's not going to be that.
Because of so many cores?
Because no, that's where the catch is. Now he's saying because there are so many cores. Okay. Now look at this. There are two GPUs which NVIDIA is providing. One GPU has, let's say, 24 GB RAM, but only 3000 cores. And there's another GPU from NVIDIA where you have 8 GB of RAM, but you have, let's say, 12,000 cores. Which graphic card is expensive? Which one? Because I've already biased you, or
You've already said.
I've already biased you, right? But this seems counterintuitive, right? When you look at CPU, your octa-core is expensive than dual core and so on. But can you guess the price difference? How expensive the first one is going to be? The first one is 4 times the second one. Because, and what is NVIDIA known for? GPU, not RAM. You see where NVIDIA is making money? Because it knows that if you want to run a bigger batch size, if you want to train your networks faster, if you want to run a faster game with a higher resolution, you need more RAM, not more cores. Today graphic cards are already at 3000 cores. Like you have, how many cores you have on your phone? 8 core? Or a good CPU will have, let's say, 24 cores, but we're talking about 3000, and this is the minimum at which GPUs are starting. So SIMD is not an instruction problem for us. What is the problem for us? The RAM, the space which is there in the RAM. Right? The way GPUs actually work for the convolution is that you look at your 1x1 operation. Let's say we have an image of 35 cross 35 cross 64 coming in, right? And let's say we are going to add a 1x1 cross 64 cross, let's say 128. Or let's say reduce it. Like, let's be consistent with what we know about 1x1. We use 1x1 to reduce the number of channels, right? We have reduced the number of channels here. Now what is going to happen is this 35 cross 35 cross 64 is going to be converted into 35 cross 35, one single line, and 64 of them. Right? Then you're going to take your 1 cross 1 cross 64 and treat it like an array, simple array. And this whole sequence of data is going to multiply with this whole sequence in exactly the same amount of time, 10 nanoseconds, or whatever the full cycle RAM refresh cycle is. And this it has to do 32 times, right? Each of this is going to be going to go on a single SIMD. If you have 3000 SIMDs, we are just utilize 32 of them, right? And later on we are going to see something called batch. When batch comes in, this you will be actually sending in not one image but let's say 100 images. And this operation, this particular 1 cross 64 operation has to be done on all the channels of all the images coming in, 100 images coming in. So this is not going to be 64, but this is going to be 64 into 100. Still a problem with RAM, not a problem with the cores in the GPU. Any question on this?
So RAM just stores it, right? But
RAM
processing still is done by
the GPU.
cores which
Yeah.
are done. So SIMD, the number of cores, in this case 3000, will limit
the number of operations different operations you can do,
yeah.
and the key is different.
Okay.
But in every convolution you have very limited operations.
Okay, so if we have 3000 operations, it will take only 10 seconds, 10 milliseconds. If it has 6000 operations, it will take 20 milliseconds.
Yes, because in one cycle it can only do 3000 different computations. So you'll have to wait for the next iteration. But GPUs don't work like that. If you provide, let's say GPU can do 3000 iterations in one cycle, and you are giving it, let's say, 6000. What is GPU going to say?
But the memory, it has enough RAM, right?
No. The way it's going to communicate back to you is like out of memory, which means like you are asking for memory for 6000, but I have memory for 3000 only.
Okay.
So each block gets allocated a particular block of memory, and it is going to look at from the compute point of view, not from the RAM point of view.
Oh.
It is also going to look from the RAM point of view. Let's say you want to do 13,000 operations, but in each of these you're not adding 10 billion, but let's say 100 billion. Again, it's going to come out and say that sorry, can't do out of memory.
Oh, okay. In that 3000 operation, you can specify the number of the batch size.
Batch size.
Okay. So GPU cannot generate multiple channels parallelly.
There are multiple SIMDs, so you can do multiple operations.
I mean, like we should generate a single channel and then we should wait for. I mean, we cannot parallelize channels.
No, we can. That's what those 3000 cores are for parallelization.
Okay. Then.
But each instruction is dependent on the how much each compute runs depends on the RAM.
What if we reduce batch size and increase the parallelization?
Not useful, because if you want to learn from data set, you want to read all the images as many times as you want.
So batch size should be.
Batch size is key for us as compared to anything else.
Batch size doesn't kill.
Bigger batch size.
Bigger batch size
Better. Now, use of existing channels to create complex channels instead of reconvolving. When you're using 1x1, it is acting like a DJ, as we discussed last time. Another way of looking at it, it's let's say, and look at this. Let's say you are trying to create you're trying to create something like this, right? And let's say let us divide this into some bunch of pixels. Right? This is divided into 5x5. Yes, no? And we use 3x3 kernel. So using a 3x3 kernel, let me change the color. I can detect this guy without any trouble, but I cannot detect this guy. And the reason for that is there's too much data to be processed. If you want to detect something like this, what you will have to do is to go beyond the boundary and actually get at least a 4x4 to be able to clearly map that, right? I'm just using here normal colors, so you might get a bias that you can actually do that, but it is not possible. You get this point? That if you're using a 3x3 kernel, detecting something like this is very difficult.
Why it is difficult?
Because right now what you're seeing is me drawing a particular pixel as it is, right? But we know that there's never going to be one straight line of pixels. What you will have some sort of bleeding of the same colors on this side also, and on this side also, right? Whenever I'm drawing, you're seeing this straight line. But if you zoom on top of this and look at the images which are coming, it's not a straight line, right? It's always some sort of texture of gradient which is going to get diluted slowly. So you're not going to be looking at this plus. What you're going to be looking at is this plus actually bleeding slowly outside. Right? So when that happens, it's very difficult for 3x3 kernels to look at all across. Anyways, we are going for 5x5 and higher resolution, higher receptive field kernels to basically come out of this particular problem. Remember how we calculated 11x11 for that dog teeth? That we had to zoom in and we saw how the gradient flows, right? So even if you're looking at a single plus here, it's going to be bleeding. It's not going to be a straight 1 pixel line. Now, when you want to do this and we just have a 3x3, we still can do something for our normal straight lines because there's going to be proper gradient flow. But for a complicated structure, you will have to look slightly out. So you have to go out and look at it. Now, what 1x1 can do for you is it will take one channel where this line is coming in. It will take another channel where this line is coming in. It will combine these two channels and create this. A normal 3x3 you were doing vertical edge detection and horizontal edge detection. But when you combine these channels, you'll have a new channel where the data itself looks like this. So now when the new 3x3 comes in after 1x1, you have an addition of 2x2 in the global receptive field. So if the global receptive field earlier was 5, now it's going to be 7. So now it will be actually looking at a bigger area and be able to learn this particular feature. So 1x1 merges those features together which are contextually important, and it allows the new set of kernels to look only on them. We're going to look at a very extreme case of what we're just discussing later on. Now imagine that I give you a book, let's say, you remember your CBSE exams? Let's say I give you one book only for all the subjects. So the first page is going to be mathematics, chapter 9, page 6. Second page is going to be physics, chapter 2, page 3. Third book is going to be what all subjects you had. Let's say computer science. Again, chapter 3, page 49. Then chemistry, remember chemistry? Let's say inorganic chemistry. So chapter 14, page 29, and so on. How do you think you will work with this book? There's one book. The first page is some chapter of some book of some subject, some page number. Second page is some chapter of some subject of some. You see what is going to happen? You might actually mix things also, because every page will not come with the title also. Now, see what are we doing in the network? We are saying we want to start with 32 and then 64 and then 128 and then 256 and then 512, right? Let's look at this particular stage. This is exactly what has happened there. This is a book where you have 256 kernels and you have this all of these kernels are jumbled up. They're not in order, right? No one is telling that only the first few are going to be for, let's say, part of the ear of a dog. Second set is going to be the leg of a dog, and so on. We are not doing any structured pattern, right? So this is sort of an issue, but our deep neural networks can handle this because they're computers. Our networks can still say that I'm going to be taking, let's say we are doing at this particular stage, we are going to go ahead with 1 cross 1, cross 512, cross 32. Let's say this is the operation we are going to do, right? So in that case, we have 512 kernels here, all scattered across, and we are adding 1 cross 1 to convert this into 32. 1 cross 1 is actually going to convert this into 32 subjects. It is going to convert this into 32 sequentially ordered different features. Otherwise, you cannot reduce 512 into 32. Otherwise, you'll end up mixing some part of the physics space to some part of chemistry, some part of math space to some part of physics. We don't want that. You want structured output to be there. It's going to take 512 and use 1 cross 1, and we're going to get 32 channels, and now these are going to be different contexts. And this is what helps the later kernel to look on top of this and work out a complex feature out of it, right? We had vertical line here, we had a horizontal line there. In this 32, we are going to get the plus. We had an angle line here, we have this angle line here. This is going to give us something like that. So it's going to make sure that all those features which are contextually similar are going to be combined into one particular channel, and a new kernel which is going to be coming here is going to be looking at the complicated feature like a plus or a cross or different texture and learn from that. Another example would be, let's say,
sorting happens
because of the 1 cross 1.
But
Back propagation is going to help make sure that you're not messing up. Yes. For example, we have this arc here, we have this arc here, we have this circle here, we have this part here, we have this part here, right? All of these are structured in different way, and these are some of the examples are from 512. 1 cross 1 is going to link all of them and create some reason. Let's say there was thumb here. Let me see if I can draw a thumb. It looks like a thumb, right? Now it does. Okay, thumb is a bad idea. Let's say there's a nose, right? And let's say this 1 cross 1 combines nose with it, right? And does not do this. So maybe it's actually doing something like this. Back propagation will not like this. It's going to say that it's not making sense. I'm not sure what are you trying to draw. It has to be contextually linked. It has to be spatially together. The spatially also these things are not going to be together, right? Nose is somewhere else, eyes is somewhere else. We are not yet there to make the part of the face. When you're making part of the face, you have that receptive field where you can see both the things together. But if you combine this right now, where your receptive field is just good enough to just look at an eye and not eye to nose, then this is not going to make sense. So in that case, backpropagation is going to say, not making sense, please do something else. So every time you're going to be checking every single variable and move it slightly and see if it works or not. We had a few questions on that.
When we are combining like the 32 from 512, so every time on each channel it will check go to back propagation, like check everything and then decide. If it is not right, then again it will keep checking till we are not getting right combination.
So we have 1 cross 1 cross 512 cross 32, right? These many times it's going to check every single time.
Okay, so it will go back.
It will go back and check. You remember your model dot summary? If the model dot summary says that you have 2 million parameters, your backpropagation is going to check 2 million times every single variable, which makes it 2 million checks every single backpropagation step.
So if we have 10 layers before, it will do all like
Every single parameter, every single batch.
okay.
Right? And since we're talking about batch, please make sure you understand this. Let's say the batch size is 100 and you have 1000 images. So going through 1000 images is called epoch. If the batch size is 100, how many batches are going to be there in one epoch? 10 batches. 10 is the number of times back propagation will happen.
So every
Batch, yes. Now, why do we need batch? We are going to cover this later on also, but let me give you some sort of idea. Why do we need a batch? Let's say if I ask you, what do you want to eat for breakfast? 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 What do you want to eat for? What should I order now? Order? Not possible. Keeping everyone happy. You think, do you know how much operation is going to go behind this? We're going to take a list, ask everyone, okay, you want idli and you want this. How many idli you want? So you're going to say, I don't like sambar from that restaurant. I don't like sambar from many restaurants. So I want specific sambar. Then that white chutney comes. At some restaurants really good, at some restaurants not good. Kesari bhat, if you want, if you go to MTR, best. You take kesari bhat from anywhere else, it does not taste like that, right? And I like, let's say, omelette in the morning. You see the combination which are going to come in? So the amount of effort which is required to keep everyone happy is not going to be there. But if you see, some of you said idli. If I can average out this order, right? If I average out order, and let's say there's one gentleman who's saying, I want English breakfast, and see that that is an outlier, we are going to not consider outliers. We are going to see what generally people want, and we are going to say, okay, abolish 370, or maybe just order idli. So this is why we need a batch, right? Now think from a network point of view. This is a network. You send in an image of a cat. What is the network learning now? How a cat looks like. So it's going to tell you that this is a cat or a dog. Let's say it was telling you dog. What are you going to say? No, this is not a dog. This is how a cat looks like. So this is the loss for you. Go back, train yourself with this. Next time you send an image of a dog, what is the network going to tell you? It's a cat, because this is what you've trained it for. You have to make it balanced before you train it. Image augmentation comes in, and we have many algorithms like recap. Then we have mix up. There are many algorithms. We can fix that. We should augment them more, right? So when you're not asking it to learn for a dog, then, and this is exactly how we used to study for our CBSE. You have a chemistry exam, you're going to learn everything about chemistry. Moment the paper ends, we'll forget everything about chemistry. Next time you're looking at a paper of physics, you're going to read everything about physics, and next day you have forgotten everything about physics, right? Because we are studying that one day by one day. If you were like, or if you know someone who's a 10-pointer, they would have studied every single subject every single day, and does not matter which paper, even the paper is shuffled, they will not have any problem. And this is why if you look at good colleges, the exams are not for physics or chemistry or mathematics, they're combined. You're going to be asked one question, one full day, which will have everything involved. And this is very well known in Stanford and MIT. For example, the question is going to be that there's a powerful space aircraft which has to leave Earth. This is the chemical composition of some particular reaction. You have these chemicals, and this is the amount of energy it can release. This is the weight of the aircraft. This is the amount of distance it has to travel. How much amount of fuel it should carry. The question looks simple, but now you have to look at the chemical composition. You have to figure out how much weight of the explosive is going to give you what kind of thrust. You need to know the physics, because now you're going to calculate the what is it called? Which velocity? Escape velocity, and also and distance. You see, everything gets involved here. So when you want to do something like this, you have to do batch processing. You have to learn subjects in batches. You have to make sure that the concepts are actually getting linked together. Right? And again, if you think about this, that if you are just sending, let's say, 5 images, cat and a dog, an elephant and a frog, and let's say car, you have only one examples of each. You can't generalize that. We want generalization to be there. Right? If I just show you something at once and then you are never shown that thing again, or after quite some time, you're going to forget it. Let's say you're looking at a new species of animal, right? You have never seen that animal. You will have to see it at least 3-4 times from different angles to make sense of what that whole thing is. And that is why we want a batch. In a batch, let's say we have 100 images and we have 10 classes. Each class will have 10 examples. So you're going to say, this is in general how a dog looks like. This is in general how a cat looks like, and so on. Right? You get this point? Like the first time the note came out, the new currency notes, If you have seen those nodes, I'm sure that you will actually take 3-4 more steps to make sure that you're not confusing them between that node and how a different country similar color nodes look like. If you go to Southeast Asia, many nodes are pink. Especially if you go to Hong Kong, the 10, I don't know what is the currency, 10 Hong Kong dollar is pink there. It looks very similar to the 2000 rupee note we have. So first instant, you're not going to say that. After looking at it quite a number of times and noticing some of the major features, you're going to be deciding that, okay, this is not actually Hong Kong currency, but Indian currency.
So,
And how do we decide the batch size?
How do we decide the batch size? Batch size is linked to the money in the bank, GPU. GPU is going to say that that batch size don't work.
So if I have 1,000 images, good for me if I have a larger batch. Suppose MB is not a problem, then I can say, okay, batch size should be as much as large.
As high as possible.
So if I put 100 as 1,000 as a batch size, so then each sample is going, each observation is going one time.
Yes.
Is that good?
That's good. That's a good thing.
But that will lead to overfitting.
No,
No?
no. We'll see that. In fact, there are two domains of science here, not science, but there are two kind of companies which are trying to do that. One company is pushing for batch size, and another is pushing for learning rate and other hyperparameter optimizations. Right? Which companies are pushing for batch size?
More GPU.
Google, Amazon, everyone is going to push for bigger batch size, because bigger batch size means more AWS, more Google Cloud Space. And then we have LR and hyperparameter optimization. Who are pushing these? Poor people. We don't want, right? So there's a Dawn benchmark. You're going to be, and this is where, if you've seen the School of AI discussion right now, and everyone is hyperactive because they want to solve the assignment 14. Assignment 14 is, you're not yet at CIFAR. You're, from assignment 6, you're going to be at CIFAR. Right? Right now, you're going to be taking a couple of hours to train the network. The assignment which they are solving right now is that they have to train CIFAR to 94% accuracy in under 100 seconds. World record right now is 94 seconds at 45 seconds with 8 GPU. Their assignment is 1 GPU. So that is where the whole world is going. That you have to literally, like, in 1 minute the whole training is done. But AWS will not like that, right? If you look at Dawn benchmark, which is where for what these guys are actually planning. So we are going to compete in the Dawn benchmark next year. You see this? 45 seconds. Look at the amount of money you spent. How do you understand what is happening here? Can you drive a Ferrari today? Of course you can. You don't have to buy a Ferrari. You have to rent it. Get someone to get Ferrari in front of your house, sit in the car, take a photograph, upload on Instagram, you're done. That is anyways what you're going to do if you have that car in Bangalore, right? So you don't have to take the whole GPU for, see what you're doing here. You're taking V100s. These are one of the best GPUs, most expensive one. We have DGX also, but like for our category, this is expensive one. And you're using 8 of them only for 45 seconds. You're going to end up paying 11 cents. Not that, even AWS also, right? This is AWS, 6 cents. So of course, Google and these guys will not like that. They bought it at a much more expensive price, right? You will not like let's say you own a Ferrari and I take it for rent, and the rent comes out as 500 rupees. You'll not be happy. If you know, if you've seen Porsche Cayenne in India, there's a Porsche car, like huge SUV like. You know how much the tire, let's say there's a tire puncher, how much you have to pay? It does not have a tube. You have to change the tire. The tire costs 75,000 rupees plus the pickup and drop charge. So it's going to be somewhere 1.5 lakh for a puncher. So GPUs and AWS and all, they're not going to like this. Okay, why do we not use a 1x1 kernel to increase the number of channels? Not true. We can use 1x1 to increase the number of channels, but you need to know why are you doing that. Right? This is very important, because people, what you're going to do, if you're confused, you're going to write a network and you know that you have to go from 32 to 64, you'll remember just that. They'll have to go from 32 to 64, 128, and you're going to be using 1x1 for increasing the number of channels. Bad idea, very, very bad idea. 1x1 is not used to increase the number of channels. Having said that, you need to know why are you doing it. So whenever you see in any code that we are using 1x1 to increase the number of channels, we would have used 1x1 to reduce the number of channels first. Right? The kind of algorithms you're going to see, which in this specific case, especially for the 1x1, is going to look something like this. You have 512 channels coming in. right? Your 3 cross 3 has to be now 3 cross 3 cross 512. You don't want that. But you have 512 channels also coming in, and you also want 512 channels to go out. You don't want to reduce the number of channels. What are you going to do? You are going to use 1 cross 1 cross 512 cross, that's a 64. Then you're going to do what? 3 cross 3 cross 64 cross 64. And what you're going to do now? 1 cross 1 cross 64 cross 512.
Which operation happens for?
Sorry?
Here you have 3 cross 3 cross 512.
Yeah, so I can do this 512 cross 3 cross 3 cross 512 cross 512,
Yeah,
and I can get this,
yeah.
or I can do 512 convolve by 1 cross 1 cross 512 cross 64, create 64 channels, then use 3 cross 3 cross 64, 64 of them, then use 1 cross 1 again to and 64 because I have 64 channels coming in, and use 512 of them to get my 512 channels back.
Why we are
Oh,
doing this?
512. Look at the number of parameters he used. 512 versus 64 cross 64 plus these guys also, but they are like peanuts because you're multiplying them with 1 and you have multiplication of 9 here.
So we need to normalize it, right? Before doing this thing.
Yeah, normalization is going to be there for all the steps.
That could lead to high
But
errors.
if you increase the batch size,
1 cross 1 cross. Yeah, tell me.
the back propagation would, the number of times the back propagation happens will reduce, right? So we need to
Repeat that.
if I increase the batch size, let's say we have if the number of images are 1,000, and if you have this in a GPU and make the batch size as 1,000, and let's say you had run for 20 epochs, as of the number of times the back propagation happens
Hmm.
would be only 20, versus if you had a batch size of 100, you would have 200 times back propagation, which means that you would be learning more, or the network would be learning more.
You're saying I need to do more back propagations?
Would we need to? I mean, if every batch will result in a back propagation, and if you increase the batch size to the size of the
I'll answer that question. Let me just fix this calculation. Give me 1 second. So we are looking at 1 cross 1 cross 512 cross 64 cross 2. We have two of them, if you remember the image. Right? 1 cross 1 cross 512 cross 64, 1 cross 1 cross 500 cross 64. Right? And then I have only 3 cross 3 cross 64 cross 64. These are the number of parameters I have. Right? And in the other case, you will be using how many? 3 cross 3 cross 512 cross 512. You see the gap? This is what? 2 million. This is what? 100,000. That's the gap. So now when you add the load because of batch normalization, or not going to matter a lot. Sorry, you had a question now. You're saying that okay. So we are going to cover this in SGD, a stochastic gradient descent, and why we do exactly what we do. I'm going to give you just a small pointer. Now, what happens if you have a small batch size? This is the whole piece of cake or the whole data set you have. You're just picking a small part of it, right? And the logic of SGD is, right now what I'm saying is going to be null and void once we cover SGD, because technically I'm not correct in what I'm saying right now. When I take a piece of cake or when I take a part of a database, we are saying that this is a homogeneous entity, which means this part of the database represents the database, which may be true, may not be true. And this becomes truer and truer if the batch size increases. Right? If, for example, if I pick 4 Indians, do you think they will represent the whole of India? Right? You have now Kashmir, you have Northeast, you have Kerala, you have like all of these states, right? We have to pick a bigger bunch which can represent them. Even if you do that, do you think they will represent the whole India? No, then you have to go for the religion part, you have to go for the food habit part, you have to go for the ancestry part, you have to see how pure were they, how indigenous were they, and so on. Like if you go to South India part, the people in South India, they have far older DNA of the subcontinent as compared to people in the North India part. So, and we are talking about making it homogeneous. So the homogeneity is required, and homogeneity is going to be there for a bigger batch size. Now, the concept is that if your data set, if the batch you're picking up is homogeneous or it's reflecting a database, then whatever you're learning from that batch size is something which can be used for the whole model.
Right.
But if the variations are too many and your batch size is small and you're picking only a small variation of those and you're learning based on that, and all Indians look like Chinese. Let's say I'm starting from northeast.
Okay.
Our network has to now forget that and learn something new next time.
So essentially, it means that you don't need to do so many back propagation to correct your.
Yes.
Uh,
Yes. So basically, this is what you're doing. Up, down, up, down, up, down. In fact, this is the problem we are going to fix also. You're going to be moving in the wrong directions a lot. This is the wrong direction. We need to go only in this direction. Bigger batch size is going to move something like this. In fact, longer ones to make it consistent.
So batch size should depends on inter and intra class difference.
You remember the discussion we had? Batch size versus good learning rate. So the two fight. One way is to just use a big batch size and go ahead. But we are poor people. So we are going to go ahead with alternate strategy where we do not have to increase the batch size by that much. When we are saying bigger batch size, we are talking about batch size of 32,000, right? This is not in our capacity. Like there are papers by Facebook and Google which says train the whole ImageNet in 1 hour. And like all Facebook terms and conditions, there's a star mark go at the bottom when we are using 2568 GPUs of V100. That's a very small part again on the Facebook paper. If you use these many GPUs, you can go with 32,000 batch size and the whole image set can be trained in an hour. And these are not our papers. We are looking for this kind of paper. Spend $0.01 and train the whole image net. Right, or like a Flipkart sale or something like that. So both the ways are possible, but we are going to prefer the LR rate.
I'm saying optimal batch size should be something like 2 to 3 times multiple of number of variations in data set.
But that is not.
Inter and intra-class.
So it is easy to say, but when you are saying number of variations, you are basically talking about the information entropy, and it's very difficult to calculate. Information entropy of an image is very difficult to calculate because very subjective. It's not difficult to calculate, but it's subjective. We'll not know what it means, right? For example, if someone asks you how much I love you or how much you love me, and you say 4, what does it mean? And this is what is going to be the answer for information entropy. So based on how subjective you are, that number might change.
Yeah. So I didn't Google like why 1 cross 1 is used for increasing the number of channels, and I didn't get a definite answer. So is it because the redundancy increases as like if you're moving from you have 64 channels and you want to increase it to 128 for 1 cross 1?
I didn't get your question.
So like 1 cross 1, so you feel it that to increase the number of channels you first reduce it and then 3 cross 3 cross 64. So like what if I were to directly increase the number of channels, say 64 to 128 using 1 cross 1? So does that increase the redundancy in the?
It increases the redundancy in the model, and you may want that in a very specific scenario, and those scenarios called super resolution. We are going to cover this. It's called pixel shuffle algorithm. We're going to use 1 cross 1 to increase the number of channels. That's what I don't want to introduce that because then you'll think that you can use it to increase. So our law says that we are not going to increase it till we hit this algorithm, and then we see that only in this case we are going to be. How many of you know what is pixel super resolution? How many of you don't know what is super resolution? Okay, you've seen that movie. In fact, many US-based movies where on a CCTV you're looking at a criminal, and then you zoom on that criminal. The criminal is wearing a glass. You can then zoom on a glass and you can see a bullet going, and on that bullet you can see a fingerprint, and a fingerprint you can take a DNA out, and so that is what they are trying to show as a super resolution. Like you can literally do an infinite zoom. Now through deep neural network you can do a zoom up to 8 times. You're not there like fingerprint and all, but 8 times is possible. And this is in fact, you'll be surprised to know, like our company works with CBI and a lot of crime branches in Bangalore, and this is what they come to us for. We are doing super resolution for them because the kind of cameras which we have in India are really bad. So they will come back and say that, and this is funny because they will sometimes come with this kind of face, literally, and they say, can you convert this into a big face? No, you can't. You have to have some data before you can convert it. But if you have a bad face, you can literally convert into a really good face.
Super resolution is increasing the pixel density in that particular medium.
Yeah, but it's not just increasing pixel density. It is learning. It has some intuition about how it should be increased.
Okay.
It's not a simple pinch zoom.
Yeah.
Yeah. All right, so why do we need an activation function? Now these two questions are linked to why actually we need non-linearity and all. So we are going to cover this again later on. We need activation function to provide a decision-making power for our DNNs. We need to make sure that they have some sort of communication. So I like to use the word communication because otherwise it's very difficult to explain. Non-linearity is basically asking you to create some sort of communication of yes and no. Some way of saying that information can flow, information cannot flow. And ReLU does that very easily, right? You have a clear demarcation of what information can go forward, what cannot go forward. To provide non-linearity, another way of saying the same thing. When you provide non-linearity, you're basically saying that for some input coming in, output may not be consistent. That is what non-linearity means. Right? For example, if I give you 5 rupees, you give me 5 rupee back. When I gave you 5 lakh, you just disappeared. This is called being non-linear. So everything has a value, and we have a value in our ReLU which says that everything which is negative is just going to be disappeared. Now, why do we need non-linearity? Now, if you think about the kind of textures we are making, kind of patterns we are making, they're not linear. We are trying to make an arc. When you're trying to make an arc, it's not a straight line. You're expecting a deep neural network to learn about an arc. Let's say a circle, it's x square plus y square equal to, let's say, some radius, right? And when you talk about parabola and other equations, you think that this is not a linear equation. You're asking it to learn itself a nonlinear equation. So it will need nonlinearity inbuilt, so it can actually utilize that particular fact. Now, sigmoid activation functions are not used because they cause gradient vanishing issue and they cause the gradient explosion. Now, we're going to go deeper when we cover activation functions. What is gradient vanishing? Which means the gradient which is flowing back is 0. Gradient explosion means it is 1 or more always. Like it's a huge value. And why 1 is bad? We are going to get to a particular number which is 3.946343229 and so on, right? This is the number we want. The gradient which is coming back is 1. You're saying please add 1 or please subtract 1. You're going to see that it's not going to do anything. It's just going to shuffle. It's a huge number for it. We want to send 0.1 and then 0.01 and then 0.01 and so on. But right now it's coming as 1 and it's always 1. It's not reducing. This is called gradient explosion. You're just sending every variable to some other country every time you're doing your backpropagation. Now, which activation function we should use? ReLU, right? The default. Now let's start today's session. Now today's session is an architectural basics. You have any questions?
Sigmoid is also used in almost all CMOS.
Sigmoid is also used?
ReLU and sigmoid. In general, last they have used.
No, sigmoid. Not used. Do not use sigmoid. So unless you're using RNN or LSTM, you're not going to be using sigmoid. And we had a specific point in the last session also which said, and in fact I made that point also clear, sigmoid is not used in convolutional neural network as an activation function.
So it is used in fully connected.
No, not there also now.
It's not there because earlier for binary classification, I've seen some examples with sigmoid.
So you need to understand, batch normalization was invented in 2015. The first time any DNN was able to actually run a network was 2015. The first time 1x1 was used as a convolution to reduce the number of channels was 2015. First time dropout was introduced was 2014. We are talking about a science which is like 3 or 4 years old. So when you go online and look for the blog, they might be using some of this and show it to you. So you should. That is why I recommend not to look at any resources. You are going to find the links directly in the assignment or in the content which we are publishing. For example, as you were trying to search online, why we do not use 1x1 to increase the number of channels, you'll not find answer for that. Every time any content is made, I have to go on this website called Archive Sanity.
But even in your code, you use some sigmoid binary before flattening, after flattening.
No.
Sigmoid activation.
Softmax. So this is a website which actually publishes the papers which are only in the computer vision machine learning domain. It's called Sanity Archive, and it's called Sanity Archive because the actual website is Archive. Archive is maintained by Cornell University, and every day there are like tons of papers which are released. The papers which you're seeing right now are only for the last 1 week.
Softmax is just sigmoid that in multiple times using for multiple outputs we are using when it is.
Softmax is activation function?
Yeah.
No.
That's why I'm not sure about it.
These are just this week's paper. And it's not done, like it's an infinite scroll. And all of these are just machine learning, computer vision, very specific to what the stuff which we are doing. Every single paper is in relation to what you're learning. I'll cover that again for you on the sigmoid part. Okay, now architectural basics.
I have one question.
Yeah.
We always multiply with the point one next point one. Why don't we come the other way, the point 001, then keep reducing because the difference will be less, right? When you start doing it from point 0001 and then point 001, we can do so. The difference will be very minimal when we start doing it. We always do with point one and then go with point 0.
Now the problem is that when we cover loss function, you're going to look at it. Most of the time when you go online, you're going to be shown this kind of a loss versus parameter kind of graph. We have a loss here and we have this W here. And you're going to be saying that we want to arrive at this particular point. In fact, nearly every single time you're going to see any loss function online. In fact, I can do it for you now. Let's say we go online and we search for loss function DNN. You see these curves? This one, this one. Right? Now, what these are trying to tell you is that there is a point which you have to reach. There's a point where you have a particular parameter has to reach, but this is not telling you the true story. This is not a point which you have to reach. You are like a heat-seeking missile and you're targeting an aircraft. So see that the bottom part is not going to be stable. Every time you change a parameter, every time you do a back propagation, the loss function itself is changing. Why is that? My loss function is a function of all the W's. And you just change the W. If you change the W, the loss function is different. So every time you're doing batch propagation or every time you're doing back propagation, your loss itself is changing. The loss function itself is changing. So it is not a fixed point which you're trying to go and hit. It is like a heat-seeking. It's like an aircraft, and you are a heat-seeking. You're actually always trying to backflow it, and that is where the concept of momentum in HDD is also going to come in. We're going to introduce something called momentum in HDD, where every time a parameter is trying to see where my loss is moving, and you're actually trying to go towards that also. Now, from that point of view, I don't even know what is the last digit now. I have an approximate location somewhere in Indranagar. Okay, now it's moved to Domlu. No, okay, now it's moving to. The question he was asking, let's say we have 3.946, something like that. Why are we starting from this end? Why are we not starting from this end? So what I'm telling you is that these big numbers are actually changing. They're not consistent. So maybe after 100 epochs, you're not targeting that, but you're targeting, let's say, 0.960 or something. So we need to make sure that we are always in sync with what the first few digits are wanting.
And is it that small actually?
Sorry?
I mean, the shape of the loss function.
That is just one single example, and that is for one parameter only. Okay. Now let's look at fully connected layer. We are not going to be using them, but you need to know how they work. Now, first thing we do in a fully connected layer is that we take our image and we destroy it. We take a 2D image and we convert that into a 1D pattern. Right? Now, when you have converted that into a 1D pattern, see what is happening here? This is how your digit is going to look like. Right? And see, and this is something which we need to see visually. I'm going to write some number on top of it. In fact, use this only. Okay. So let's say we take yellow. I'm writing 1 only. Okay, very simple digit. This looks like 1 to you, right? Now let's make our fully connected 1D flat output for this. How many pixels do I have in the image?
6.
Let's say we remove this. I have 25, right? So I'm going to make this 25. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Let's say 25, right? Now, when I convert this to a 1D array, I need to look at which pixel now? First pixel, second pixel. Right? then first, second, third, fourth, fifth, sixth, seventh. Basically, after 5 pixels. So 1, 2, 3, 4, 5. After 4 pixels, sorry. Then 4 pixels again. 4 pixels again. This is 3 pixels. 4 pixels again, and then 4 pixels again. Is that correct? Which means that, yeah, this is correct now. Yes, no? Now let's move our 1. We just slightly move our 1. Now if I move my 1 slightly, I'm going to again write this, but I'm not going to draw all those lines now. And let us move our 1 from there to this location. Right? All of your 1s are going to be shifting now. Right? Now let's rotate our 1 a bit. Instead of this, someone is writing in a cursive writing, and this is the kind of 1 which is coming in. Right? The new pattern which you're going to learn is going to look somewhere like this. Right? You see the problem with converting it to 1D? First of all, you're saying after some pixels there's going to be a pixel, white pixel. After some pixel there's going to be a white pixel. After that pixel there's going to be some white pixel. And then you're asking after how much difference, how much gap. And that is not stable. Let's say you're asking that I've called you for a party and you're asking for direction. I'm saying that go in that direction and then take a left. You're asking how much. I'm saying it may be between 5 km to 10 km. When you start from a particular location, after 5 to 10 km, take left. Where?
Is it also because
Between 5 to 10.
Is it also because so now one the yellow one which you draw, it had like a 4 pixel intervals between. So like would there be another digit which will have the same?
Which will have a similar digit also. So see, when you convert your 2D information into 1D information, it's very difficult to imagine. Another example, I'm telling you that from here to airport, every 7th building, notice the color and and record 100 buildings from top to bottom. So 100 cross 100, right? 100 cross 100 is 10,000 buildings, let's say. So from here to airport, look at every 6th building, record the color, 10,000 of them, and then make a building out of it or make a painting out of it. You see how difficult it is? Very, very difficult for any network to figure out what the hell is happening. And the moment you rotate it, the whole pattern is gone. Every single pattern is gone. Now, in fact, I made that the last pink one because I wanted to do this. This is not 1, this is 7, which means this is going to be color, this is going to be color. Now, not what the network is going to see. Most of the details are matching, except for the initial few ones. It's going to say this is 7, or it's going to say it is 1. And it learns that, it's learned that. So if it says this is 7, then this is not going to be 1 ever. And if it says this is 1, this is not going to be 7 ever. So fully connected nature of fully connected networks are going to take a 2D information and divide it into 1D. And that literally destroys the complete location information we have. We have to have the location capacity that we need to know how the feature looks like, right? We are talking about digits right now. Now imagine how an eye will be converted into 1D. You see that every single eyelash is going to be in some different location. The whole image is just going to be very, very bad. And this is why fully connected layers have never been able to go beyond MNIST. Right? And MNIST and all, and in fact CIFAR and ImageNet database also, people were using fully connected layers because there is one way for us to solve many different problems, and we're going to see that. But since 2014, you're not going to see any neural network using any fully connected layer in the way which I'm describing as of now. There are other use cases which we'll see, but not in any other case. Are we fine on fully connected layer? Why we don't use them? And computationally expensive. It's super heavy. It's super heavy. The amount of parameters you're going to add is like exponential, and we're going to see that in a moment. Now, so this is what we saw. Now, this is how fully connected layers are going to be shown to you. Those lines you see, they are weights. So every time you see a line, you're going to be shown a weight. So let's say we have taken our initial image of 32 cross 32 or 28 28, which is MNIST. We are going to convert our MNIST into these neurons. What is a neuron? A pixel is a neuron. In our case, every single pixel is a neuron. So we are going to take our image and convert it into a 1D array, right? So 28 cross 28. First step is right. Then we are going to say I need some specific hidden layers. How do we decide hidden layers? Same concept which we have covered. More number of kernels for more number of features required. If the network has complicated images, then more number. Again, similar concept goes here. So if your data is complicated and you have a lot many features, you will want a better representation of the data internally. So you're going to go with a large number of kernels here also. And every single one of them is going to be connected to every single one of them. And this line is actually saying that it's a weight actually. Every single line is going to be a particular weight. 0.3, imagine another number 0.4, another number minus 0.3 and so on. And what are we doing basically? We are going to be multiplying this number with 0.3, this number with 0.4, this number with 0.3 and so on, and going to add all of them and put it here. So this is how fully connected layer is going to work for us. This is just saying in this shown in this particular way. Now you will get confused whenever we see convolutions, because in convolutions those lines don't mean the same thing for us, right? You need to understand this, because images should not confuse you. You are seeing these lines and these lines are weights, but when you're looking at convolution neural network and when you draw something like this and we say our 3x3 is convolving on top of this, let's say, right, and I draw 3x3 here and you saw these lines, and then finally it gives me a single 1x1, right? These lines are actually lines, they are not weights. What is weight here? The kernel. The kernel has 9 weights here, right? So don't confuse these lines with the lines which we are using in fully connected layers. Now this got replaced, basically this is fully connected layers got replaced with our convolutions, and since then we have not gone back. Now before 2014, this is what was happening. We are looking at VGG network right now. You have an image coming in, right, and this image is now being convolved with many kernels. Look at something which is actually set by VGG and people are using it today also. You see the size of the channels changing? Do you see the thickness of the channel changing? Right? You're seeing a block 1, block 2, block 3, block 4. A similar architecture which we discussed also last session. Like we have 4 blocks. You see the size dropping here? This is where the max pooling part is coming in. Now 1x1 is not invented yet. Neither is batch normalization. So those things are not included in VGG original architecture. Right? You have 64, 128, this is 164 already, 128, 256, 5 and 12, 5 and 12, and then we have 1024 also here. This needs to be 1024. This is how the original network was. Is this part clear? Now you see this thing. 2014, VGG added a fully connected layer. This was the last time anyone was seen using a fully connected layer. After that, no one has used it. Now this is how the network actually looks like in the backend. We have again 224 image. 224 is a normal size of the ImageNet competition images. So ILSRVC or ImageNet database is bigger images, but first step anyone does is to convert the image into 224. Is it part clear? Now you need to be cautious about one thing here. If you are going to start with 224, your network may have a, let's say, accuracy of 77%. However, if you start at, let's say, 299 cross 299, what do you think your accuracy is going to be?
Just 1 second. 224 is the original image pixel quality.
Original image is 600 something. We are scaling it down to 224.
So you have got a normalization there.
Sorry?
Image resize.
Resize.
Just resizing, normal resizing, right? The first step in old days, people will go to 224, 224. But let's say you just sneaked in your paper, and in your paper you actually started with a resolution 299, 299. Let's say you pick the exactly same network. What do you think the accuracy is going to be? The accuracy by default increases, because you have bigger image, bigger textures, bigger area to look at, right? So accuracy itself is going to be 79 or 78 depending on what you're looking at. So whenever a new paper comes out and say that we are state of art, you have to go inside and see what is the size of the image they're looking at. You have to be state of art at 224, not 299. So whenever a new paper comes in, please keep that in mind. Now same steps, 64, 128, 256, 5 and 12, 5 and 12, and this is where the fully connected layers are coming in. Right, and the reason for that is, first of all, VGG is one of the best architectures. People in fact today are also using it, and it's a part of many encoder decoder architectures. And the reason of that is that it's very simple. First architecture in the world which says use only 3x3. You want 5x5, you can just make it to 3x3. Right, you want 7x7, you can still make it to 3x3. First network which actually added proper positioning of max pooling. 1x1 is not invented, so they have not used that particular part, but otherwise just 3x3 is a max pooling. Very, very simple architecture. Now we need to remember that this came in 2013. The research was in 2013, and 14 is when the competition was held, right? How long do you think people took to train this network? 6 months.
I mean,
You're not talking about V100s or 1080 Ti or 2080. All of this is like last 2-3 years. Time is moving so fast that we're actually forgetting in 2014 what kind of GPUs we had. We had GeForce, right? And they're spending 6 months, and they have already done so many changes.
one training 6 months,
The full network end-to-end training.
not like correction and all those things.
No, no, no.
Fine tuning, just one.
Including fine tuning.
Okay.
Including fine tuning.
Getting to that.
Getting to that accuracy. Now, and we are going to see this in today's lecture also, that when you make changes, you don't make all the changes simultaneously. Let's say this is a network and I make 5 changes to it and my accuracy has increased. I'm happy, so I will not think about it. But let's say my accuracy actually reduced. Which of the 5 things caused that issue? And this is how generally we code. We have a problem, we are writing a code, we have a good solution, we are going to add that solution, ye bhi add kar deta hu, ye bhi add kar deta hu, ye bhi add, and then finally crashes. And we have no clue what the hell has gone into that, right? So that is one big problem. So they added a fully connected layer. Now let's see what happened because of that. First thing which happened was that they came second. GoogleNet was the first one, which is the inception architecture. They came second. And let's look at the parameter. Now when you're adding 3x3 convolutions, look at the number of parameters you're adding. 36,000, 73,000, 147,000, 200,000, 500,000, a million and all, right? These are numbers we are playing. Look the moment you add a fully connected layer. Do you see that number? This is like you've gone on a buffet, you have paid 1500 rupees for the buffet, and now the waiter comes and asks you, sir, would you like a wine? And you said yes, proudly. He comes back, gives you wine, you're happy, and the bill is 1.5 lakh. The wine you ordered was like 4,000-year-old something. This is what is happening here. You spend like 20 million parameters for the whole network, and in the last 2 networks, you're spending 118 million parameters. You see that how much bulk it is adding? Now, had they removed this by something called global average pooling, we are going to see that later on, it actually increases, and the number of parameters you're going to add is close to 4,000, 5,000. Very, very few parameters. Let's say you have this idea. You go back to them and tell them, please do this. What are they going to tell you? Can you go back in time again and 6 months, 6 months back and then tell us, because it's going to take 6 months for us to train it again. Right? So we're talking about times when the GPU resources were not really available. Now, we need to look at softmax. The way you call it is very simple. Keras.layer is a softmax, but we need to see exactly what this guy is doing. And I want to add this as an emotional point to you. Like, you need to understand what is happening from emotion point here. Now, so I'm going to divide this class into two teams, team 1 and team 2. Okay. Now, team 1 made a particular network, trained it on the images which is coming in, use a good GPU, all the good practices, etc., etc. Team 2 was lazy, and you guys stole my network. I was not in the class, you just put a pen drive and stole my network. I forgot to add softmax, you added softmax. That is the only difference in our networks. Exactly the same network. What is softmax? Softmax is e raised to the power 5 divided by e raised to the power 5 plus e raised to the power 4 plus e raised to the power 2. You get that value. E raised to the power 4 divided by e raised to the power 4 plus e raised to the power 2 plus e raised to the power 8. You get that value and so on. Right? Both of us are a student of some professor. We go there and I tell them that my network is telling me that this image is a cat with the accuracy of 5 divided by 5 plus 4 plus 2, which is what? Around 45%. What are you going to say? 71%. That is your network, which you stole from me. In the second case, I'm going to say that my horse, we can talk about this also. This is 65%, 8 divided by 8 plus 2 plus 4, 8 divided by 14. But we have 4 divided by 14 also. Now, what is 4 divided by 14? 2 divided by 7, and if you look at it, let's say around 15-20%. Let's say that number. I'm going to say I'm getting around 20% error because I'm saying this image is actually a cat. What are you going to say? 98% confidence that this is a horse, and 2% that it's a cat. Softmax is going to take my numbers and it's going to scale them up. It's going to separate the numbers as far as possible, along with making the sum equal to 1. So it looks like probability. It is not probability, however. Please remember that. Anything which sums up to 1, it is not probability. Let's say I have 1 rupee, I give 50 paisa to you. What is the probability you have 50 paisa? Not 50. You have 100% 50 paisa. I just gave it to you. So anything which sums up to 1 is not probability. We like to call it a probability, right? So whenever you go online, you search for softmax, you're going to see it's called softmax probability. Keep in mind it is not probability, and this is very important, especially because GDPR laws are now coming in. In GDPR, people are expecting that you're going to look at a network and going to tell what your network is actually doing.
But actually, probability adds to 1, na?
Exactly. So everything which adds to 1 is not probability.
So does this also add to one on the ultimate?
This adds to 1. If you add all of these numbers, it's going to be 1.
Like
That is how we are
we
calculating.
we can't do more than one.
No. Now, so this case looks fine. Let me change the case and then see your reaction. This is confidently telling it's a cat, right? And you're okay with that. Let me change the scenario a bit and see what happens now. Let's say this is your medical report, right? This is saying no cancer. This is saying cancer type 1. This is saying cancer type 2, right? If my doctor was using this report, my doctor is going to tell you 45% chance that you have cancer, 40% chance that you may, 45 that you don't have cancer, but 40% chance you have cancer. What is your doctor going to tell you? 71% chance there's no cancer, right? He's going to look at the majority and tell you you have no cancer. Which doctor would you want? My doctor or your doctor? Why my doctor? You stole my network and you wanted to be happy. Softmax makes us happy. It takes the same number and divide that. In fact, we can apply this here also. No cancer, cancer, right? So no cancer is coming out as, for you, 98%. For me, cancer is still coming as 20%. Now softmax is used because it's actually going to create a large difference between the numbers, right? And that makes us happy. That's all. There is no scientific, there's no technical benefit of using softmax at all. You can replace it by any function you want. But we use softmax because it does that to our network. And why are we doing this? Everything has some sort of history. There was a time in 2010 and 11 when to advance machine learning, the ILSR-VC competition was started, the ImageNet competition, right? Now imagine that you want to promote electric cars, you start a competition, I come in with my Ferrari, with gas and diesel and all, and win the first 2 years. What are you going to feel? You forgot to mention that you only have to use machine learning algorithm, or you only have to use electric vehicles. You called it electric race. So I said, I'll add an electric ignition motor, but everything else is just diesel. I won the first 2 years. So the kind of algorithms we were using, we were trying to make sure that we can compete with these guys in some way. For example, top 5. ImageNet is still top 5. So when you see accuracy of 96% on ImageNet, that is top 5, which means it's going to tell you out of these 1000 classes, this image may be elephant, aeroplane, cow, frog, or maybe a dog. So this is coming from the old history. We wanted to compete with machine learning, computer vision algorithms, and if we actually do something like that, our numbers look better. But this is not adding any value. Please never use this if it is going to be about medical or health scenario, right? Imagine this particular number again. This is your model telling you, I do not see anyone on the road. This is telling you, I see a woman with a bicycle crossing the road. You are Uber. What are you going to say? I want to use softmax, go ahead. And then there is a case which is going on. What Uber has to go in the code and explain? This part. It's expressivity. You have to explain this is GDPR. In the code, you're going to say, I wanted to feel happy, so I used softmax, but my network was not really doing anything there. Now, look at the last scenario also. We are writing 4 and 4 here because the image taken from internet and we are writing integers. But when we are working in machine learning, there are no integers. All of these are floating points. No two floating points are ever going to be same. Ever. No two numbers are ever going to be same. And these numbers are after like multiple billions of operations which are coming out. One number is going to be slightly more than the other number. 4.0000 Calcutta 0 and then 1. 3.999 in Afghanistan 9 and then 9 again. These two numbers, when we are going to send to softmax, we're going to say 0.50001, other number is going to be 0.49999. And what is going to happen? You're always going to be looking at the first prediction. You're going to take a call. Cancer type A, cancer type B, right? Your network says cancer type A. Your doctor starts diagnosing for the cancer type A, right? You don't know what is softmax doing? No, you know the formula now, right? E raised to, what is the formula for, how do I calculate 0.49? Right, if you want to calculate this, we are going to say e raised to 4 divided by right? This 1 is coming from this guy, this 4 is coming from this guy, and this is coming from this guy, right? So basically we are just going to change the numerator. So sometimes it's going to be e raised to the power 4, and sometimes it's going to be e raised to the power 1, and this time it's the e raised to the power 4, right? All the three which we have in denominator is going to be there in the numerator also. So which means that if you add all of them, it's going to sum up into same numerator divided by same denominator, 1. That is why it sums up to 1. But everything which sums up to 1, it is not probability. And there's one more reason for that. How do you think we are getting this number? What is this number? What exactly is that number? It is a channel value. It is the amplitude of what the kernel is seeing in the image. Your kernels are seeing those kind of amplitudes. Your kernel is seeing texture which are very similar to dog. It's a cat, yes, but it has legs, it has similar texture, it has similar fur, and all of that is actually coming out like that. Right? So you cannot not say that there is no cat inside. You see, it's a deep neural network. It's going to tell you in quantity. How much you love me? It's going to tell you 42. So it's not going to say yes or no, because it's seeing those things there, right? The ear is there. If you're only shown a part of an animal, it's very difficult for you to say what you're looking at. And this is also what is happening here. So you have to fix this. You have to fix this bias of the network where it is trying to see a dog and a cat as a very close animals, because if slightly the cat is looking at backwards, suddenly it's going to start telling it's a dog. We don't want that. We want network to have a large gap in these numbers. But because of softmax, you're going to see the gap is already 50%, and you're not going to take any action on that, which is bad for the network. Right? There are two networks. There's one network which 99% accuracy, another network which has 99% accuracy. Which network is better? Let's say both are using softmax. You have no clue right now because I've not given you any other information. Let me create a bias now. Class A and class B, there are two classes. My network 1 is going to predict class A with 99% accuracy, and and class B with 98.9% accuracy. And network 2, where it's going to predict class A with 51 and 49. Basically what we are saying, whenever an image is going to come in, it's going to say class A and class B with only small gap. Right? Both the networks have 99% accuracy, which means both of them are going to correctly tell you for the data I have. But the gap for the network A is going to be 2%, gap for the network B is going to be 90%. This network is going to be 90% confident that this is not class B while it is saying class A. This network is going to be saying this is class A, but the confidence is only 2%. You definitely want the second class. You definitely want the second network, right? We are looking at the accuracy here, or prediction, this value basically, right? We are saying that our network A looks at class A and says this has 0.52, and looks at the class B and says this is at 0.48. Everything has to sum up to 1, right? Because softmax. So the gap here is only a very small gap, right? Now remove the softmax part, because we are actually talking about the amplitude gap here. So this amplitude gap is only 0.2 for one network, and for other network the amplitude gap is a lot of gap, it's a huge gap. Let's say this is 0.9 gap. So you want a network which is very confident, which is saying that this is definitely not a cat, this is definitely a cat, this is not a dog at all. The gap has to be more, right? And you want to train a network where the gap is actually more. Is this part clear? How do we do that? We are going to see that, but this is very, very important. That is what is it. Okay, so there's no probability on this page, right? We're just calling it probability because someone just called it. That's all. For example, you know about a Xerox machine? You've seen Xerox machine? They're manufactured by? Not Xerox anymore. So that is what is happening here. Someone called probability and we just call it is not probability. These values mean something, and we need to work on those values and fix them. Okay, now we are short on time, but if we actually miss something, then I'm going to cover this again. Now you remember your assignment 2? In assignment 2 we used this particular network. You remember the network we used, the bad network? And all of you said that because we are using large number of kernels and all, right? But the moment we added our ReLU, it actually goes to 99.4% validation accuracy. But 25 million is like huge number parameter. What we're trying to do right now is actually work for your assignment. So what we're going to see in the step of these 7 codes is how do we step by step actually go at a network where we can train it under, let's say, 15 epochs or maybe even shorter number of epochs and get 99.4% accuracy in less than 10,000 or 15,000 parameter. That's what we're trying to achieve here. Now this is the first DNN code which is what we are going to start with. Now what we are going to do here is very simple. The old network which we saw. This is one of the assignment which I had shared, right? In this network, here starting with 32 kernels, 3x3 size. Yes, no? Yes. How many outputs I have? 10 outputs. I want 10 outputs. I have 10 numbers. So I'm going to convert my these 32 channels into 10 channels immediately by using 1x1. We use 1x1 to reduce the number of channels, right? And then I used a huge kernel because the channel size was 26x26, and I just wanted one value. So I used 10 kernels again, 26x26. Not an ideal network. Many ways to do it. Another way of doing it, just remove this 10-1. We don't need that 10-1 here. I can use my 3x3 32. It's going to give me a channel output of 28 or 26x26. How many of them? 32 of them. I can directly use 10-26, which means use 10 kernels of size 26. So 26x26 cross 32 now. But I use 1x1 to reduce the number of parameters a bit because this is still going to add a huge number of parameters. You see the 67,000 values I'm adding. Now this network which has 68,000 parameter, now if you train it, what we're going to see that after 10 epoch, we are at somewhere 99.62, but that is not the accuracy we are interested in. That is what you are going to look at the book and learn all the answers. We are interested in the validation accuracy, which is at 98.29. Now this is not good for us, so let's start with a network where we can actually write an architecture which is similar to what we want. Now this is a network which is something very similar to what we have discussed, that we are going to use some 3x3 kernels and then we are going to convolve by right. So 2 layers of 3x3 followed by max pooling. Max pooling not, let's see in this particular code. Yeah, there's no max pooling here. Max pooling is okay, good. Now max pooling we have covered already. Yes, no? Okay, so what we have done here, we have written a very simple network here. We are adding a max pooling after 3, 5, 7. You see this network? We are adding max pooling after the receptive field of 7. Now after that we have again, so what we are doing, we are starting from 32, going to 64, going to 128. We are doing a max pooling. Then we're going to 32 again, then 64, 128. How do we reduce the number of channels? By using 1x1. Then we went to 64, 128 again, and again use 1x1 to reduce the number of channels. Now here my resolution is 7. The channel size is 7. So I have to use a huge kernel size 7x7 to make it into 1 digit here. Now this is what we are going to do till you're not exposed to global average pooling. If you know what is global average pooling, you can use it at your end, but I'll recommend not to do it because we want to see exactly what global average pooling is going to do later on. Till then, you're going to be dropping to some particular resolution and then use a huge size kernel here. Is this part clear? The architecture is clear? Yes, no? Whenever you are writing a code, the documentation I'm expecting from you is that you're going to say the size of the input channel or size of the output channel. Mention that, what are you showing, and receptive field at that particular point. Is the part clear? Every single time you're going to write a network, that is documentation in the network I'm expecting from you. Now when we write this and when we train it, first of all we are going to see in the model lot summary that we have added around 200,000 parameters, very far as compared to where assignment wants to be at, right? And if I start training, I see my network is going to 99.61, but the score is not still there. I'm still at 99.18. But this still gives us a direction that we are in the right direction. The number of parameters are more and I need to increase my accuracy slightly. Is the part clear? Now had I added here tons of different stuff, right, what we are going to do in next step, if you have added so many stuff, so many different steps right now, we'll have no way to increase it or reduce it. Will you go back home and take a tetanus injection today? What if you fall on something which is rusty and then it actually impregnates your skin? Will you go and take injection which you take after dog bites you? What if dog bites you? Will you take crocin today? Any operation you do on your own body, you do it after some sort of symptom. And that is what we have to do with the network. Don't add something because you think it's good. Crocin is good for health if you have fever or paracetamol and all the other things you can think of, right? So this is the first network we have trained. We are getting a 99.18. We added max pooling in this. Let's look at the second network. This is third DNN. I'm not sure why the sign in is required every time. Okay, so now in this network, what we're going to do, we are going to now play with the number of kernels we have. Why? Because that is the first important target. The target was to be below 20,000 and we are right now at 200,000. So let's see what is the least kind of number for us where we can go and still be around the same accuracy. Because if we actually go beyond two below the accuracy, then we know the kernel placement, this architecture is not right. So first we have to make sure the architecture is correct. So what are you going to do when you write any network? You're going to fix the architecture. Now the architecture I've used, I'm not going to change it now. That is exactly the same architecture I'm going to play around, because if I change that, everything else is going to change now. The same architecture, if you remember, what we have done here, we have changed the kernels here. I'm going at the other extreme. I'm going just with 10, 10, 20, then 10, 10, 20, 10, 10. Right? So you need to look at the high extreme and then you need to look at the lower part. That what exactly is the play? How much actually can I go low right now? Now when I'm doing this, what I'm going to see is my parameter at 10,000, really good. That is close to what I want. If I look at the accuracy, I'm still going at 99.33. First look at the accuracy part. 99.33. What does it mean? In the other architecture, I was at 99.6, which is a better network.
We can't say that. We have to check the validation.
You can increase the epochs.
Yeah, it would be better, but we have to see the validation accuracy.
See the less numbers.
Now, this is where your thinking has to be slightly different. What I would say is that this network is better. Right? Why I would do that? Because right now I'm at 99.33 here. I have a scope of increment of 0.67 here. Right? In that network, the scope was 0.39. I'm looking at scope, I'm looking at potential right now. This network has potential, I can push it to be higher. But that network had this gap, but the validation accuracy was 99.18. Here my validation accuracy is 98.84. Right? What is the accuracy there? 99.61. And this was the gap. What is the gap? If you calculate what is the gap, what this gap looks like? 43, 0.43. Right? What is the gap we are looking at in this architecture? This is 0.37, right? And these are similar numbers. Like you run this network again in a similar epoch, numbers might come out differently, right? So these are similar numbers. That is what I'm looking at. I'll look at these numbers as same or similar numbers, which means that given if I can change something about this network is at least going to be as good as the last network. What will make me not say this? Let's say this was 96. If this was 96, I know this network is not going to go anywhere. Is this part clear? This is how you have to see what your network is doing. You have to see the potential. What we are seeing right now is my network has potential. This has only gone to 99.33. I can push it to go to 100. And hopefully that push is going to be translated into my validation accuracy also. My validation accuracy is right now 98.84. I can push it 60. I can push this guy also 60. But I need more because this gap is not going to take me to 99.4 in the easier way I'm looking at. So we are trying to look at how can we do the next step. Is it part clear? Now what we're going to do, now we are going to add batch normalization. What I'm going to do now is like take 5 minutes and open all of these so we don't have to go through this again. Okay, so this is a fourth network, and what we have done here, I think, is that we have added a batch normalization, just batch normalization to see what we are going to, what is the increment we can directly get. Now, I have not covered batch normalization for you. I'm going to give you a brief pointer of what it is. Yes. So you see exactly the same architecture, same number of kernels, same location of max polling, nothing is changing. I have just added batch normalization here. Now, MNIST is a very easy data set. It is a very simple data set. Effects of batch normalization and all is not going to be really evident on what exactly is happening. But the moment you go for a complicated data set like Ceph-R or ImageNet, the changes are going to be drastic, right? Now, if I see this model now, first of all, my parameters have increased. I have now 11,000 parameters compared to 10,000 something I had early on. So batch normalization is going to add its own parameter. And now you see these two things, trainable parameter, non-trainable parameter. So there are two parameters, one which is trainable, another which is not trainable. What are non-trainable parameters? Non-trainable parameters. What are trainable parameters? Trainable parameters. What do we mean? Non-trainable parameter is a calculation based number. Some number which is output of some calculation. You cannot modify that. But using that number, you're going to be modifying something else. Right? So non-trainable are some sort of values or variables which are calculation based. You're going to be storing them in the network. Now, when I run this network, the first thing I see is that my network is again at 3.99.39. It's not drastically changing, right? It's again, last time I had 99.33, this time I have 99.39. My validation accuracy, however, slightly up. From 98.84, I'm at 98.97. Not a huge gap, but slightly up, slightly helping me. Now, had I already used batch normalization in the first step itself, I'll not know whether it is helping me or not helping me. You have to go step by step, and this is what we have done here. Now, in the next code, okay, before we do that, I just want to cover this particular part with you, which is exactly what batch normalization is. Now, I'm going to simplify it so we understand this faster, but when we have a full session on batch normalization, so we're going to go over this again. Now, this is how your features look like, right? This is the first part of the date we covered. Yes, no? Now, these may look like good to you, but our network is not really happy with them. And the reason it is not happy with them can be made evident the moment I convert this into a black and white image. The moment I convert this in black and white image, the first thing you should notice is, can you differentiate between this kernel and 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 this kernel, all the kernels I'm drawing, can you differentiate between what they're trying to do?
Slight difference in gradient in some places.
Right, as compared to these guys, like we clearly know what is this guy doing. We definitely know what is this guy doing, and this guy and this guy and this guy. Right, so what has happened is that these kernels are trying to do something, but their amplification is not really high. Right, now, for example, if I just stopped reducing my voice and finally go to a very low volume where you can't hear me, so we can't do that. We can't have some kernel which is screaming like Arnab Goswami and some kernel which is not speaking at all. We don't want that. We want to do some sort of equalization. You have done equalization. When you take images at night, you go back, you change something about the image to make it brighter. That is exactly what batch normalization is doing for us. Exactly the same stuff. It's the easiest way to understand batch normalization. What it does, how it's doing, we're going to go deeper once we cover batch normalization, but this is what we're trying to do. Some channels are not getting at the same amplification. Why? You have taken a photograph of a dog in at night. Vertical edge is coming out, right? There are two vertical edges which are coming out, right? One vertical edge looks like this, and another vertical edge which looks like this. The amplitude is different now. So the channel which you're going to create will have lower values. Now the next feature which is dependent on this to make the eye of a dog is going to say what? This is an eye and this is not an eye. That is also an eye. An eye is an eye. It does not matter what lighting condition you're taking it at. Or it's a white dog or a black dog. An eye is going to be an eye. So in that case, the channel does not have enough amplitude. So what do we do? For the whole batch, we are going to be normalizing all the channels, which is basically equalizing all the channels. We're going to say, this is not black, this is not gray, but both of them are like this. You understand the point? We're not going to say this is black and this is gray. We are going to say both of them are like this specific gray. So all the channels will have a similar amplitude. Everything is going to be at a similar level. Now my features can learn on top and have a very simplified understanding of what features or what values are is what we need to work with. So that is what batch normalization has done for us, but we have seen that it's not adding a lot of improvement, and the reason for this is MNIST is a too easy database to actually modify with anything. It is too easy for us to work on all this problem. But the same thing we are going to do with CIFAR also, and uh, your intuition will be much clearer with CIFAR. It's a much more complicated database. Are we clear on this? Now, after this step, what we are going to do, we are going to look at the fifth parameter. Now, you see in the fifth network, my network parameters have increased. What I wanted to see was maybe see, I have the luxury of making network changes now, right? In this network, I've added what? In the fourth network, what have I done? We added batch normalization, right? So my batch normalization is done and my network architecture is sort of done. Now, what we are going to do in the fifth network is change the kernels. Network with more capacity should give us better result, right? So I'm just changing the number of kernels. Earlier I had 10, 20, 10, 20 kind of kernels. Now I've changed it to 10, 16, 32, 10, 16, 32. The increasing, reducing architecture we discussed, right? Again, same 10 epochs. I'm just going to look at 10 or 15 epochs maximum. My network is at 18,000 parameters, still less than the target which I had. Nothing is changing, and I'm going to look at now. Another thing which is important for you to remember is that when you train a network, let's say this particular network, you see the accuracy. This validation accuracy 98.79, this 98.97 is of which model? By the way, how many models do you have in this on this page right now? You have 10 models. Model 1 is not same as the model 2 you have trained in the epoch 2. It's not same as the model you have trained in the epoch 3. When I'm saying not the same model, I'm talking the parameter values you have. Right? And every time you check your validation accuracy with these models, it's going to come out different. Right now, you're hoping that your 10th model is going to be the best one. Right now, you're saying your 10th model is going to be the best one. Right? For example, you're looking for a job and you're saying the 5th job is going to be the best one for me. How do you know? Sorry? You might have actually got the first job with the first offer itself, right? So we are not really sure the last model is good for us. So what you have to do is to add this small snippet of code which says validation data equal to x test, y test. That's all. When you do that, you're going to be checking your validation accuracy every epoch. Now look at the validation accuracy, right? It hit 99.07 just, or in fact 99.12 in the fourth epoch itself. And we are right now, what is the change we have done? We have gone with higher number of kernels here, still making sure that we are still less than the target accuracy, but we have gone with slightly higher number of kernels here. Is the part clear?
So I've used validation data with the model before. So I've always had this doubt wherein, so if you just train the model first, explain and white it, and then you try to evaluate it, wouldn't that be better? Because as you're training, you're trying to evaluate it each epoch. So by the time again when you try to evaluate, you would have already seen the validation data.
No, seeing validation data is not learning from it. We don't do back propagation when we do validation test.
And one more. So there's something called as validation split, wherein you split the training data again into test and training. So is that helpful anyway in like increasing the accuracy or
No, no, no. Actually, there are three things which are coming from, and this is from the competition and assignment history, because of which we have three things actually. We have our training data, we have our test data, and then we have our validation data. And then you can do subsplits again. Now, training data is a set of images given to you with the labels also. Validation data set is a set of images given to you with the labels. You are supposed to run your model on top, train on training data, but run on validation data and not train on training validation data, and then tell the score. Right? Your score may be 100% here, but you're going to be telling the score on the validation data. How do you know you're not lying? How do we know anyone is not lying? You could have trained, mix this also, right? You can train on the validation data also. So you create test data where you do not provide the labels. We do not provide the labels. You provide the image, ask people to run your network, and this is what happens on Kaggle and other competitions also. You're going to be given three data sets. Validation is for your own test. It's like a mock test. Before the CAT exam or any exam, you're going to be giving a mock. This is a mock test for you. And then you are going to be actually giving the test, and the scorecard is likely going to go for the evaluation. So your labels or your predictions directly going to the Kaggle competition, right?
So when we are training our own model, when we split our on our own, so data gets shuffled. So the numbers that we see are huge. Like the difference is huge.
We're going to see that. We don't make we make sure that your validation remains validation on your training remains validation. Training remains training, and you're going to see some parameters we have to look for when we are actually creating this data set. Now, what you're going to see is that I hit 99.12 here in my model, but then drops. The validation accuracy drops, right? And something strange happens now. Look at the numbers here. First of all, I'm going to see my model accuracy is going to tell you my 99.05, which is the last validation I've already done. So no need to check again. It's exactly going to be same. But something strange is happening, and unless this happens, you're not going to be doing the next step. What is okay? What do you notice from this?
Loss is decreasing, but
It is
accuracy is not there.
0.998 with training.
What do you call that?
Overfitting.
You're seeing overfitting now. You're seeing now that your model where you have increased the number of kernels here, right? That is the only change with it. We've increased the number of kernels here. We had batch normalization already. This model is very capable. Look the number. This is very good number, 99.8. But look at the gap. We are seeing what? Overfitting. Is it part clear?
How do you say it is overfitting?
We are seeing that. So okay. Overfitting is subjective. Overfitting is subjective, right? Now, a good way to understand this is like, let's say something which is subjective is fairness of skin. Now, do you think you are fair or I am fair? I'm asking you.
You are fair.
Do you think I am fair or she is fair or he's fair? I don't know. Out of them, who's fair?
She is fair.
So that is subjective, right? For me, I think he's fairer. So this is subjective. For example, if I ask someone, in fact, girls will know this better. They know that their weight has increased by half a kilogram. Girls know that their weight has increased by half a kilogram, 1 kilogram. I've seen women telling that I feel half a kilogram heavier today. I don't know whether we can do that or not because we are not that conscious. We have built that subjectivity. Now here it is overfitting for us. The reason being we are looking at a target of 99.4. If my network is at 99.8, even if I push it to 100, this will never go to 99.4. I can only translate that point to increment into validation accuracy if you're not fitting the overfitting problem, if you're not fixing the overfitting problem. Right? So overfitting is very subjective. Let's say you're looking at a network, or let's say this is a problem where everyone else is getting 94.
No, I am asking how do we measure it?
There's no measure for it. Just the difference between this, yes. But this is also not true because let's say if the world is at 94, your network is at 99.05, then this is not overfitting for you. Then suddenly this is the world's best network. So overfitting is very, very subjective.
No, the difference should be less or more.
More. This should be higher than this. As long as this is higher, this is overfitting.
The difference between them should be tending towards minimum or should be.
That is subjective.
So same is
Sometimes it
applicable
is,
for
but
test
sometimes it
data,
is not.
like the accuracy which we are getting here, and when we are
Same is applicable for test data. Let me give you a good example. Here, in fact, you're going to see networks where overfitting in MNIST is going to be somewhere around 0.1. A very good network will have overfitting of 0.1 at 99.6 or 99.8. Then we have networks in ImageNet where model accuracy is going to be 99.9 and your actual accuracy is going to be 77. And this network was not overfitting in 2014. Now we are at 86. Now suddenly this network is overfitting. Tomorrow if someone creates a better network which can actually take the validation score to 90, this is going to be overfitting. You see this is changing, the trends are changing. So overfitting is very subjective, but anytime you have your validation or training accuracy, test accuracy lower than the training accuracy, it is overfitting. We don't call it, you call it like after some time.
Overfitting is good if you are the best.
If you are the best, yeah. Alright, so what we are seeing right now is overfitting. How do we fix overfitting? How do you fix overfitting?
Augmentation.
Some sort of augmentation or dropout or something of that order, right? So what we are going to do, in fact, before we fix that, we are looking at a sixth network now. Now in the sixth network, what we are going to do is again take the same code, don't change the code. If you change the code, you don't know what is helping you or what is not helping you, but add dropout now, right? And the location of dropout right now I'm adding just before the max pooling layer. I've added my dropouts here. I've added my dropouts here. Now look at the network. My model parameters are not going to change. Dropout does not change or add any parameter. The moment you add dropout, you're going to see your overfitting has gone. Do you notice that? You are at 99.49, this is 99.3, you are at 99.51, this is 99.08. I see something here, 99.55, 99.23. So we had 0.7, 0.6 kind of overfitting there. Now that is not the case. Now, but I'm not still getting my 99.4 accuracy. But then if we run for slightly longer, at 21st epoch, we are at 99.4. And this is not a fluke, because after that, we may get 99.4 again, 99.42 I'm getting again. So we are there, but slightly something is off, right? At 21st epoch, we are able to reach that point. Is the part clear? Yes, no? Right? So and we are at 18,004 parameters, and we are getting a 99.4 validation accuracy. Now, what is dropout? I'm going to take a small, just to explain what dropout is, I'm going to take a very small example. Okay, first of all, what are these guys? Pixel, right? What is this guy? Pixel of the channel, which happens to be hidden in terms of fully connected layers. So most of the dropouts are going to be shown you like this, right? Which means what are we doing? We're dropping the pixel. Is that clear? Right? Higher channel, let's say you're talking about layer number 5, where there each pixel is how big? The global receptive field, that is exactly how big that is. So when you're dropping up, when you're adding a dropout at a layer where your receptive field is, global receptive field is 11 cross 11, and you're dropping that pixel, how many pixels of the original image you're not seeing? 11 cross 11. So what you're trying to do is to train a network by saying that even if a frog's leg is missing, it's still a frog. Even if the head of a person is missing, it is a head, it is a human. You may be watching Game of Thrones, right? Even if an arm is missing, it is still a man. Kill Bill. So there are many things which can be just trained to a network, and we can actually force it to learn something like that. Now, every time a person wears white shirt is Rohan. That is overfitting. Now, if you want to train a model which does not recognize that, what are you going to say? You're going to delete the white shirt part. Now the network is going to be forced to look at something else. Now I'm going to be using one example a lot of times, where is that you are trying to train a data set on frogs and other things, but one of the specific frog of a particular category had a BMW logo next to it. You forgot to look at that, and it took many photographs from many different sites. Network has decided to learn that BMW logo. Every image has that, your validation image has it, your normal training image data has it. Everyone is happy. It is that frog, and every time that image comes, it looks at the BMW logo and says that frog. No problem at all. Till a BMW car actually comes in, and you're going to define that car as a frog. How can we get rid of this particular problem? By dropping the logo. When you drop the logo, you're going to be training a network which is going to be looking at lesser feature and actually try and expect the similar accuracy. That is what happens in dropout. We're going to go much deeper than what we just discussed.
What those are essential may also be get dropped out.
Exactly. Now, look at a very good example of this is how a cricket team should be managed. Drop Virat Kohli. Drop Bumrah. What are you going to tell your team? Your position is not consistent. Does not matter who you are. And on top of that, you will have to figure out a player who can actually fill in that particular position. Right? And this is the kind of team we have today. People are replaceable in team. We have multiple wicket keepers. I've not seen a era of Indian cricket where we had multiple wicket keepers who are batting good also. Now we have like competition going on between them. We have bowlers. So Ashwin is not in the cricket team, and it's a very different weird feeling because I've seen him doing real wonders, right? So there are many players who are there ready for the team, and this is there because the team is actually trying to do a dropout, but not with Virat Kohli and these guys. Fortunately, they get injured, so we have a dropout there also. Now, if you remember the 16 years of Indian cricket time when Tendulkar was there was no dropout. Every single time you had Tendulkar in the team, you were dependent on him. Had you dropped him out many times, or had he got injured many times, you would have other players who are coming in and saying that if this guy is not there, we can perform better. So we actually want to drop everything or every single feature. It may be important also. We're trying to make a network which can actually look at not that part also and then look at that, and maybe figure out this is this is a fox versus a, let's say fox versus a dog, right? Very difficult for humans to figure out, especially if you're not looking at the face. But there are some body changes which can be seen and which can be observed, and you can say it's a fox and a dog. Now, if you hide the face of a dog, how can you hide a face of a dog? Occlusion. It is just crossing a particular forest. There's a tree. The face is not visible. Network should not get confused anymore, and all of that we can actually fix by using something called dropout and other augmentation strategies we are going to see.
I have a question here. In ReLU also, if we like negative weights become zero, is it same as dropout?
No. There, that is a pure communication. There you're going to actually look at the kernel.
Dropout is good sometimes.
Sorry?
Dropout is good sometimes.
Dropout is good. Sometimes we are going to see that what times it is not good. But so it has fixed our issue, and we are at 99.4, but we have to go to our higher number of epochs, and that is not something we want. Now what we have done here in this particular case, this is 7th number, we have just changed our training cycle. We have just changed the way we are training a network. This is the only bit of code we've added. What are we doing here? We are saying that, remember our discussion, we want to go to a number 0.3456789, but our learning rates were fixed. Every time we were giving a feedback of 0.001, we want to change that. Now we are saying every single epoch, please change the number at which you are training. You see this learning rate 0.03, now it's dropping and dropping and dropping and dropping and finally dropping again. Now look at the validation accuracy, 98.45, 05, 16, 25 is consistently increasing, 27, 31, 24, 21, 42, and we're done. 14th epoch, we're done. So this is the learning rate change. What we have done here is every time, in fact, think of it like this, that you can only move 5 feet. If you move only 5 feet, you cannot sit on this chair. You cannot go anywhere actually. You need to be precise in location and how much you want to move. And that is the only thing we have changed in the network. Exactly same network, same batch normalization, same number of kernels, same position of dropout, nothing is changed. The only thing which has changed now is what? How we are updating the model. And how we are updating the model is now through a particular function which is telling us the learning rate.
So that takes in account global and local minimum.
Yes, it takes into account that how you actually want to. So the only thing which is changing now is the learning rate, and it consistently increases. If you draw a graph of this also, you're going to see that it's actually increasing pretty consistently. Is the part clear? Now if you run it again, but again, if I stop here, then I'll end up reporting 99.3. So don't do that. Whenever you're at 99.4, save that model as the best model and report that. And that is what is done here also. I again hit 99.4. So it's not a fluke. We are hitting 99.4 again and again. We hit here again. So not really bad architecture. Now in the next two codes, I'm not going to cover this these two codes. I've actually just played with the number of parameters again. You can open this guy if you want. I've just changed the number of parameters in the network and an architecture a bit. Now based on a new architecture, what we are hitting is 16.6 thousand parameters and 99.46, 11th epoch. And again, reducing the number of parameters more. You want to push yourself. You want to see what is the extreme you can go, right? And this is the extreme at which I go. Someone in the EVA went really extreme. 5,000 parameters, 10 epochs, 99.4. I'm going to share that network with you also, but you can really go at extreme. So in this network, what has changed? I have added dropout at every single step, right? There I was saying I know where I need to add dropout. That is insane. We don't know where we need dropout. So add it at every single layer, right? That is where you add dropout. And I'm changing nothing else actually. Number of kernels might be slightly different. Number of parameters have reduced. 16,000 now. Same way of increasing my validation score. I'm hitting 99.4. In the 11th epoch, that's 9.46. Right? Is that right? Okay. Now let's look at the assignment part. Now we have covered some of the concepts till now. We have covered how many layers, pooling layers, 1x1, 3x3, receptive field, softmax, learning rate. These are some of the points which we have covered, right? Now what we want from you in the assignment is you are going to be doing a third assignment again. You're going to be doing a third assignment again, but this time in 4 steps. Is that right? Okay. First step is basic model. No dropout, no batch normalization, no playing with learning rate, nothing. Fix the model, fix the architecture, how you want to build a network. Once you fix the architecture, you cannot change that. Which means the location of max pooling is not going to be changed, the number of layers you are using is not going to be changed. Right? So you have one single file. In that one single file, there are 4 steps. Step 1, architecture is fixed. Step 2, you are going to fix the kernels. Step 3, you're going to be fixing what? Maybe adding a batch normalization or dropout, and then step 4, finally arriving at this particular 99.4% accuracy, 15,000 or less number parameter. Is it part clear? Number of epochs, 15 or less. Try to do it as good as possible, but again 20 epochs is also fine, but try and do that. You can do it and actually in around 15 epochs. Now one single file, somewhere it says 4 different files, but this was for EVA 1, but don't make 4 files, just make 1 file. So one single file divided into 4 blocks. First block, simple architecture, no max pooling, of course is going to be there, no batch normalization, no dropout, no LR changes, nothing special there, right? Simplest architecture you can think of. You think that you want to go from 32, 64, 128, that is the architecture to test on. So that is going to tell you this architecture is going to give you 200,000 parameter. Then you're going to tell yourself, no, this is not what I want. I'm going to reduce the number of kernels. Then reduce the number of kernels. And then again check what is the accuracy your network is giving you, right? Then add batch normalization and then see whether your net model is overfitting or not. Like if I see that you're adding dropout and you're not seeing overfitting before that, your assignment is wrong. You understand that? Right? Because it has to make sense. Imagine that we are doctors and I'm a senior doctor, I'm looking at you and I'm trying to train you. I'm seeing that you have fixed a horse. You have given horse tetanus injection as a step 1. It's not the right thing, right? It should be at a particular step. So you have to add dropout or whatever you want to add at a stage where it is making sense. I'll add my LR changes when I know my model is better. My model can learn. Right? I'll add batch normalization before that. I'll make sure the model is actually trainable. These are the steps you're going to do. Now every time you can change as many steps as you want, but you have to make four codes. The final code is 15,000 parameter, 99.4% accuracy, 15 or less number of epochs. First code is the basic model. So go in steps.
So you just told us that use dropout only when you observe overfitting in a model. So like batch normalization is usually used when a particular kernel amplitude is that high, right?
Repeat that.
Amplitude of the particular kernel or text pattern is that high. We won't be able to see in your stuff. So that's the part I'm kind of confused with.
Yeah, where to add batch normalization?
No, that I got it. Dropout only when your model is overfitting, but batch normalization.
MNIST will not be able to see. But the moment we go to CIFAR, what you're going to see, without batch normalization, your model cannot be trained. MNIST is too easy a data set. Right now, we're actually using a nuclear missile to kill that small fox. But the moment we move to CIFAR, your batch normalization is going to be very clearly visible. Anything else?
How do we say model is fixed?
Sorry?
Usually, what are the things that we say model is fixed? Like if kernel size doesn't come, if we change the kernel size, then it means model is fixed or not.
When we are saying model fix, your kernel size is fixed, which is 3 cross 3. We always use 3 cross 3. Number of kernel is not fixed. This you can change. But location of max pooling, number of layers, and their position is fixed. Basically, convolution, max pooling, convolution, max pooling, and so on. If you have done this, this is fixed. This cannot be changed. You can change the number of kernels you have inside. You can add something to this. You can add batch normalization. You can add dropout, and so those things you can do. The optimizer outside, you want to use SGD, that's fine. You want to use Adam, that is also fine. Those things are outside. Now you might want to use either of them, but not going to matter. SGD is the king of all the optimizers. So, but you may want to try it out just for the heck of it, right? So you can change that. You can add a LR scheduler. You can add image augmentation on top of this again. All of that you can do, but this model is fixed. That cannot be changed. One quick way of image augmentation is what? Dropout. We just did. You're dropping the whole ear. You're dropping the whole eye. You're dropping the whole thing out. Even after saying that, you're going to see that we don't like dropout. In School of AI, we don't like dropout, and we're going to be making clear as we move forward that why we do not want to use dropout. But as of now, dropout is good enough for our MNIST. Is that clear? Any question?
Second on the batch normalization, in earlier class we discussed that we should increase the amplitude to make it kernel to be differentiate. Now we are saying we want to average it.
Because there are some kernels, some channels which are very small.
So then the earlier concept that we need to increase amplitude because that's why we are using relu. So that we are replacing with that transition.
No. Both of them are same concepts. In the first time when we said that we want to increase the amplitude, we want to increase the amplitude. But again the range has to be consistent, right? Earlier case we said that we want them to be between 0 and 1. But now what is happening, even after my kernels are at 0 and 1, my channels which are coming out are very small. So I'm going to change my channels now. I'm going to move my channels also in a similar range. The kernel is still there. They're still at high amplitude. A high amplitude kernel is working on a channel and then giving you a low amplitude channel out. And we are fixing this by batch normalization, by forcing this to go up. Alright. Okay, have a very beautiful day.